those stuff for that or not?
Sorry. Well, the current to voltage converter, I did mention it. I did touch it. It's a very simple circuit
Yes,
which I
sir.
mentioned that you're applying current, but because of the fact that the current would actually into the amplifier amplified, but because you have a voltage that is sorry, you have a resistor that it is the current at the output amplifier, the current is going to go across, then it means that you can get voltage. Remember, anytime you have current flowing through a resistor, then voltage develops. So it means that you're applying input current amplifies, output current, output the amplified current. That output amplified current is fed back through a resistor, which means that across that resistor you can get actually output voltage. You follow me?
Yes, sir. Yes, sir.
Good. And therefore, it means that that specific circuit can be used as a current to voltage converter. I want you guys, I'm getting the impression though that I'm not sure if it's me or, but I'm getting the impression that the level of reading that I am expecting, the amount of effort that I have done in terms of putting stuff up and the document, I'm not 100% sure. I'm not very convinced that people are doing the necessary reading, because I'm expecting if you are, there are certain things that you would have garnered, and if not, the questions will be coming. Sir, I read through this. So just like you just mentioned, I mentioned the current to voltage converter. Somebody would have gone through it and said, okay, I went and I did my reading, or I did my watching, or I did my research, and I look at the current to voltage converter, but I'm not still understanding what exactly it is saying. Could you elaborate, or I'm not understanding this particular section? Could you help me with this, sir? That's kind of the level of work that I want to see, put out at this time. Otherwise, the only thing I can do is to give you guys a test to make you guys push you guys to read. All right, so you have the. I'm gonna go back to the
Sir. Is it possible for us to like get a syllabus? Cause or
a syllabus is posted
I
in the
didn't
group. What you see? That's the same thing I'm talking about.
yeah for me, sir.
That's the same thing I'm talking about. In the Google Classroom,
In the classroom.
there is a syllabus. Anybody else have seen it?
Yes, sir. I've seen it.
So you understand what I'm saying? This is the thing that frustrates me, because I'm putting out the work. I'm putting the stuff there. And if you guys if you're coming to me at this time to say things like that, then it means that you're not even looking in terms of what's even posted in the classroom, much less to read for understanding or watch the videos for understanding. And that's kind of disheartening. Anyway, quickly, today I'm going to be looking at difference amplifier, which is the same thing as the subchapter, which we started. But we're going to do some more analysis of it. We're going to be looking at integrator, differentiator, summing amplifier in today's session. So let's jump right into it. Are you guys seeing my screen? What are you seeing right now? Just to make sure we're on the same page. What are you seeing?
Sir, it's like a Sony network.
Sir, we seen the whiteboard, Jamboard.
Okay, wonderful. All right. So you would have recognized that this board, this on the whiteboard, this circuit is what is known as the difference, not only a differential amplifier, it's a difference amplifier or a subtractor. Differential amplifier generally, a differential amplifier is any operation amplifier that you're applying different signals on the two inputs. It automatically becomes a difference amplifier. A differential amplifier, my apologies. But this network on screen is called a difference amplifier, meaning it takes a difference, or otherwise known as your subtractor. Okay? Now, how does it work? You're applying two signals. You're applying signals to both inputs. And what you want to do is to see what is your output voltage based on input voltages that you're applying. Oh, let me go back to this. Let me just do this. Make sure I'm doing this. All right. So to do the analysis of this network, to know what the output voltage, remember we're applying two input voltages, and we're getting only one output voltage. That means that we're gonna have to utilize the whole concept of superposition theorem. And I did start this the last time, so I will just quickly roll through this again, just to make sure that everybody on the same page. So here, in order to understand what's happening, what does superposition theorem speaks to again? Let me go one moment. I'm sorry.
Consider each source at a time, sir.
All right. So in order to do that, the first thing that we're going to be doing is what you're seeing right here. We're going to ground V1. And if we ground V1, it means that our input to V1 is 0 volts, right? So we ground V1. And by grounding V1, no voltage goes on V1. Which simply means that the resultant network would be an inverting amplifier. We have looked at inverting amplifier already. And if you can recall, the inverting amplifier's output voltage would be equation 1. Or where V2 is what's going in. It's an inverting amplifier. The gain of an inverting amplifier is the feedback resistor, or minus the feedback resistor over the input resistor. So it means that it's minus R1 over R2. That's the gain. But the output voltage is the gain times the input voltage. Am I correct?
Yes, sir.
Yes, sir.
Hence, the output voltage for network 1, when we ground V1, that's ground in V1, would be equation 1. Everybody with me?
Yes, sir.
Wonderful. Anybody not with me? All right. Silent mean consent. Moving all right along. So we know what the output voltage is from V2 when V1 is grounded. The next thing is to ground. So we're gonna erase this. We're gonna ground now V input V2. And these are very first part, ladies and gentlemen. It's critical that we understand it. So now we're gonna apply our voltage to V1, and we are going to ground V2. Which simply means we're grounding this. Okay? So we're over this side. So if we ground V2, it means that the voltage that is going into the input of from V2 is 0 volts. Am I correct?
Yes, sir.
Wonderful. So V1 is our input voltage. Now applying the voltage to V1 with V2 being grounded, it leaves us with a non-inverting amplifier, because you realize our signal is going on the plus input of the operational amplifier, right? So it's a non-inverting amplifier. And again, from what we know, based on what we have been doing and what we have proven, is that right here, we know that gain for a non-inverting amplifier, which is VO over Vin for a non-inverting amplifier. What's the gain again? Gain for a non-inverting amplifier, ladies and gentlemen. I definitely need to set a test. That's the only way I'm gonna get you guys to be going through this material. All right. So with this type of response continuing for the rest of this class, you know that next week Thursday we're gonna have a test, unless I'm getting the responses that I'm expecting. This is something we have gone through already. You know, I'm not even saying what we haven't gone through, but you have the info. So the gain for the non-inverting amplifier is what?
Sir, is it R1 over R2?
Plus 1.
1 plus the feedback resistor over the input resistor. All right. I'm struggling tonight. And in this case, the feedback resistor is R1. And the input resistor in this case would be R2. So that's the gain for the non-inverting amplifier. So therefore, the output voltage for the non-inverting amplifier is simply multiplying the gain by the input voltage. Am I correct?
Yes, sir.
Okay, so we're going to use the same concept for this very circuit. We want to know what is the output voltage based on we are applying voltage to V1. So when we apply the voltage at V1, that's going to cause current to flow through R1, R2, and that is going to be divided between R1 and here. So in other words, not all of V1 will be going into the amplifier at the non-inverted input. Some is going to be dropping across R2, and whatever is developed across R1, you will agree with me that that is what's going to go into the input of the non-inverting amplifier. Yes?
Yes, sir.
Yes, sir.
So it means that we now need to find what is going into, or what's the voltage across R1, and I call it Vx. The voltage across R1, which is the voltage that's going into. So we're going to use voltage divider to find Vx, because that's the actual voltage going into the voltage of the at the input of the non-inverted amplifier, and not fully R and V1 only, right? So to find the voltage, to use voltage divider, it gives us this expression that the voltage across R1 is this voltage. Is that correct? Is that correct?
No, sir. It should be.
Yeah.
Sir, it should be R2
Should be R2.
over V1.
It govern, bro. No, R1 I find, brother.
The voltage
Yeah,
across
find R2. No, R1 I find, so you'd have.
voltage across R1.
Yes, so you'd have VU. You'd have
Correct
the
divider
R2
that become.
voltage divider.
All right.
So the one where you have to find, you'd have.
That you use voltage divider, yeah.
Got to know they are top.
Yes, brother.
It's in a bro, G. That's for the top. Proceed.
On the current divider, you have the opposite one.
It's a constant.
Alright. Okay.
Then right.
Yes, sir.
What do you say? Voltage divider.
Boy, you find they use the corresponding resistor divided by the sum multiplied by the input.
Okay. Ms. Robinson, do you concur?
Sir? Oh, this is correct.
You're saying that this is correct, right?
Yes, sir. It's for current to use the opposite
All right.
resistor.
Now, ladies and gentlemen, these are the reasons why we try to use or try to teach you some of or we do some modules early, with the fact that you do the modules. And I know it's difficult sometimes, but we want you to do the modules for a lot of times for understanding, and not only just to pass, because you realize that something like networks and devices. Networks, of course, network, and of course, devices. Those are modules that are going to take you up to graduation. Agree? That's going to take you right up to graduation. All right, so now that we understand and concur, we can go on. So now we know that this is the voltage across the resistor here. That's the input voltage, right? That's the input to the non-inverting input, right? So based on this formula here, this one here, I'm going to make a modification to this formula by changing this and putting that over here. To say that the output voltage of the non-inverting amplifier is 1 plus R, and this is R1 in this case, but again, for generalization, it is 1 plus the feedback resistor over the input resistor times the input voltage. So we know that this part is going to remain because this is a gain. Yeah? And the input voltage is the voltage that you're applying to the non-inverting input. And if we know that Vx is the voltage that is being inputted to the non-inverting input, then it goes to say then that our output voltage, yeah, could be written as equation 2. Everybody see my equation 2?
Oh, so this is what you were saying last class, sir.
Yes, ma'am.
Finally get you. Yeah.
Happy that you have. And I hope everybody else. And this is what I want to reiterate. This is what I want you guys to go through. And if we do something or we did something and you did not get it, or there's something that you read or you watch, you did not get it, then you say, oh, sir, please. And I have all the time for you for that. But when, we're doing that, you don't come to class. Remember, baby and the spoon feeding I did in devices 1. We're not going to do the babies and the spoon feeding as much in devices 2. All right? So I want full participation. The only way I can get that is if you guys do your part and I do my part, and I then help you to shed some light on things that you're not understanding or you want some help with. All right? Okay. So now we have the 2 equations based on output voltages from the 2 input resistors. Sorry, the 2 input voltages, right? And superposition says what? What you should do with them?
Sum them.
Sum them. All right. So what we have done, we have equation 2 and equation 1. So therefore, the total output voltage now is V1 plus V2, right? So VO1 plus VO2, equation 1 and equation 2. So equation 1 plus equation 2 or vice versa, right? So it means that our output voltage would look like this. And if you want, you can call this equation 3. Everybody see that? Everybody see I got that? All I'm doing now is just summing the output voltage 1 and the output voltage 2 to get the total output voltage based on what superposition theorem speaks to.
Yes, sir.
Yes, sir. See.
All right. Wonderful. So that's the output voltage for this network. And now you can see clearly why it's called a voltage a subtractor or a difference amplifier, right? A subtractor amplifier or a difference amplifier, because it's showing you that the output voltage for that network is a difference between the 2 input voltages. That's what this equation is showing you. These that are in front, the voltages, are just the coefficients, right?
Yeah.
Good.
Sir.
But you can clearly show that some coefficient of V1 minus some coefficient V2 is the output voltage of that network. And that is why it's called a subtractor. Cool?
Yes,
And
sir.
I brought you up to here the last class. So after we're gonna look, one thing that I've also said is that every operational amplifier, everyone, has a general expression for output voltage. The output voltage, once you're operating as a operational amplifier, is going to be the difference between the two input voltage or voltages, which we call VD. So VD is what's going to go into the amplifier. The amplifier has a gain, which we call AD. And we know that input voltage times gain give you output voltage. But we also know that that same operational amplifier can or is or will actually operate in a common mode configuration if both inputs are seeing the same voltage. And even sometimes if the application of the voltages are not done directly or deliberately, or this way, if you're applying the voltages to be different deliberately, there are sometimes voltages that are going to be picked up by the same amplifier that are the same. So we spoke earlier in this class about things like noise voltage. And if the noise voltage is present at one input, it's going to be the same noise voltage that is present at the other input. So we would say that the noise voltage is up at both input would be common, right? So the amplifier also has that capability to give you, to operate that same amplifier. It's operating in the differential mode, but it's also operating in the common mode as well. And therefore, the output voltage for all operational amplifier, general expression is what you see here. And for your purposes, you can make your note and you can call this equation 4 if you so, equation 4 if you so choose. Now, if that's the case, we can then find, obviously, that equation 3 must relate to equation 4. Because we said this is a general, equation 4 is a general one for all operational amplifier. And equation 3 is a specific output voltage for the subtractor or the difference amplifier. So it means that this one must have some way to relate to this general output equation for all operational amplifier. Am I clear?
Yes, yes.
Crystal, sir.
Crystal. All right, so here's how we're going to link the two equations now. Because obviously we're seeing nothing that, apart from VO, that has some form of common look in terms of both expression. But there is something that we know. If you're applying a voltage to V1 and a voltage to V2, and the voltages are different, it means that we're going to have a differential voltage by subtracting 1 volt from the other. Agree?
Yes, sir. Mm-hmm.
Hence, we say that the difference voltage VD is the difference between the two input voltage. Either V1 minus V2 or V2 minus V1. Doesn't matter. Right? Voltage, magnitude is what's important. The sign really does show you that it all depends on where you're taking your reference from. So that's one thing we know, that VD equals to V1 minus V2 or V2 minus V1. All right? Yeah.
Yes, sir. Yes, sir.
All right. There's also, since it's the same amplifier, and that amplifier can have a common mode configuration, we can also find a relationship between the two input voltage. If the two input voltages are the same, then it means that the common mode voltage is going to be the average voltage that is going into the amplifier, which is this expression, VCM equals to V1 plus V2 divided by 2. That's how, remember, that's how we average things, right?
Yes, sir.
Good.
Just the two voltages.
Yes, sir.
All right. So bearing that in mind, we can go to the next slide, which is this. Thank you. Now, just backing up a little. Let's go back, since we know the equations now. If that's the case, you realize that there seems to be a little light at the end of the tunnel, because we're trying to equate this equation to this equation, right? Equation 3 to equation 4. So now, from equation 4, we can actually have some form of correlation to equation 3, because we know these two equations. We know that VD equals to V1 minus V2. And we know that VCM equals V1 plus V2 over 2. So, let's write V1, because now we want to find how these relate. So next thing we're going to do, and please stop me and ask any question anytime. So that from the previous equation, I probably should call this equation 5. Again, just for your own benefit, notes-wise. So equation 5 and equation 6. Okay? So, from equation 5, we can then make V1 the subject of the formula. Since VD equals to V1 minus V2, V1 is going to be VD plus V2. Right?
Absolutely right, sir.
Yeah.
And from this equation 6, you'd agree with me that 2 VCM equals V1 plus V2, right? From equation 6.
Yes, sir.
Yes, sir.
Therefore, we can write V2 now. We can make V2 the subject of the formula right here, which is what I have done here. So V2 equals to 2 VCM minus V1. Make sense?
Yes.
Okay.
Yes, sir.
All right. So we're going back to this expression now. So V1, we said equals to VD plus V2. Well, V2 is, that's V2 from what we obtained from above, right? And this is V2. Agree?
Yes. Yes.
Right. So remember, V2 equals to this, you know. See, V2 equals to this. So what we're doing is putting V2 with using back this expression. V1 equals VD plus V2, but we're substituting V2 as 2 VCM minus V1. Simple maths. If that's the case, it means that we can move down to here. Because now we can say, okay, put the V1s together. So if we bring this V1 over to here, it makes it become 2 V1. And that 2 V1 is going to equal to VD plus 2 VCM. Agree?
Yes, sir.
And therefore, V1 is, you divide both sides of the equation by 2, we get V1 equals to VD over 2 plus 2 VCM over 2 is going to leave us with VCM. And if that's the case, we can call this equation 7. Okay. Sorry. Now, that makes life a little bit nice and simple for us, because remember, what was our expression? You see our expression right here? V2, we know what V1 is. Now we have found V1 solely in terms of VD and VCM. So we want to find V2 likewise, solely in terms of VD and VCM. So we said V2 equals to 2 VCM minus V1. But now we know what V1 is. So we can put V1 from equation 7 into this equation. So it's going to be V2 equals 2 VCM minus V1. But V1 is VD over 2 plus VCM. Therefore, simplifying this expression, we have 2 VCM minus VCM is going to leave us with 1 VCM, right? So V2 is going to be VCM minus VD over 2. So that's equation 8, if you so choose. Equation 8. Everybody with me?
Yes, sir. Yeah, man.
Yes, sir.
Yeah.
All right.
Yes, sir.
But this is what is interesting now, ladies and gentlemen. Now we're seeing that there's an expression for V1 in terms of VD and VCM, and likewise there's an expression for V2 in terms of VCM and VD. So if that's the case, right? Hope you're taking your notes. We can jump over to here. Let me just erase this because I don't want to confuse you guys right now. So let me just erase this first. So you remember our general expression for the output voltage for the difference amplifier? You remember the difference amplifier output voltage?
Yes, sir. That we just define.
Yes, sir.
All right. So now all we're doing is just replacing V1 with the expression, what we have found VD and VCM to be. And likewise V2 in terms of what we have found VCM and VD to be. So in other words, this was V2 and V1, right? And we just put in what we just did, found in equation 7 and equation 8 into equation 3. Okay? So now it's very clear that yes, this difference amplifier can actually be written in the general form of the output voltage for operational amplifiers. Good? Now, let's say that we have the same, remember that this is the difference or the subtract amplifier. Let's show you how this now becomes important. Suppose, ladies and gentlemen, I gave you that for this subtractor, let R1 be equal to 25 kiloohm and R2 equals to 22 kiloohms. And I want, from knowing that that is the case, for this circuit, I want you to find the common mode rejection ratio of this amplifier. Do you remember what the common mode rejection ratio of an amplifier is? Operation amplifier is?
Repeat that, sir? The common mode what?
The common mode rejection ratio of an operation amplifier. Can anybody tell me what that is again?
Yes, sir. It's 20 log
The open loop gain.
over ACM.
Yeah.
Yeah.
All right, you're giving me a formula. That's not what I want.
Open loop gain over the common mode gain.
All right, again, you're giving me a formula. You're giving me a formula. I mean, I have it here now, if that's what you're trying to tell me. That this is what your common mode rejection ratio is in terms of a formula. But can you tell me in terms of words, what really is this formula saying?
Sir, it blocks
Ratio of.
It blocks unwanted signals and let through the wanted signal, sir.
All right.
Sir,
The wanted signal is the differential
sir, in
signal.
my word,
Yeah.
it's a word, it's a number that a ratio that describes how well you would pass through the difference, or block out the noise from the difference of the two signals.
All right. Good. So listen to how I put it. I say that this common mode rejection ratio of an operation amplifier is a ratio that tells you how well the amplifier will amplify signals that are different at its input and reject signals that are the same or common at the same at the input. So it rejects signals that are common and it amplifies signals that are different. It's the ability to amplify signals that are different and reject signals. How well it is able to amplify signals that are different and reject signals that are the same. And the formula for that is differential gain over the common mode gain. So, based on all information that you are given and what you do know, who wants to solve my problem for me? So it's this circuit, and I have that R1 is 25 and R2 is 22K. It's all that you've been given, and I want the CMRR for this network. How do you go about finding it? And I've given you a hint that the CMRR is the differential gain over the common mode gain. Anybody who give it 2 minutes to think about it and tell me what you would have.
Sir.
Listening.
Sir, can you repeat the hint, sir?
Everything that you need is on the whiteboard on this page right now. The hint is there. The
Sir.
values for the resistors are there.
Sir, so that means that the AD and the ACM would replace. Basically, I could replace them with the values inside the bracket beside the resistor values.
Something like that.
Basically, you kind of equate it to the general formula. But yeah.
But I have done that already with this
I
expression.
mean,
This expression does that, you know, the first expression on top of the. So now that you know that it's already been equated, how do you go about finding it, A-Pops? If you want.
Plugging it into the formula, sir. So
Okay.
ACM is R negative R1 over R2, and AD is 1 plus R1 over R2 times R1 over R1 plus R2. Is that right, sir?
Check it out now for you. All right.
Sir,
You said that
Question.
one at a time. Go ahead. One at a time.
Me, sir?
sir, was going to say you could,
No, go ahead.
after you put in the values, you would look at the coefficients. So in
All right. Simple, ladies and gentlemen. If you're given R1 and R2, put those in the formula. No, so the big formula here, you know.
So, sir, you never heard me say?
I did, but that's why I said that one at a
you
time.
want us to put it in? Oh, sorry, sir. Oh.
Yes, man, I did. So I want you to go ahead and put the values in. You know the value for R1, you know the value for R2. So I want you to put those in. So let me help you. Because you're going to take too long, and I have other things to move on to, and it's 6 o'clock already.
Yes,
So
sir.
R1 over R2, 25 divided by 22 is how much? Oh, Lord, man, you guys don't get that yet? No calculators?
1.136.
Okay, so it's 1.136. So the first part of this equation is 1 plus 1.136. That equals to what?
2.136.
All right, so all of this is 2. Sorry, my apologies. Let me do this. Good. So this part is 2 point.
2.136.
So let's call it 2.14. And then that is going to be multiplied by R1, which is 25, divided by the sum, which is 47. So 25 divided by 47 gives you
0.53.
0.5. Yeah.
And 0.53 times 2.14 equals to
1.136.
Or 1.1.
1.134.
1.14.
1.14. Okay. All right. So I'm going to the next page. So okay, and let's do this now. So we know this already, that 25 divided by 22 is 1.14, right? 1.14. Okay, so new page. So we're saying that VOT actually is going to equal to, what do you have again? Um, 2.14 again times.
2.14
Yeah,
times
it's 2.14 times 0.3 is 0.53. 2.14 times 2.14.
So when we times that, sir, we got 1.1.
All right, so we got 1.13.
1.13.
Well, closer to 1.14, sir, than 1.13.
But if I times what's the
Now round it up.
3? We can run up with 4.
So that'd be 1.13.
Exactly.
I mean, I'm gonna keep 3 decimal places. I'm still get
that's how-
1.136.
Sir, run it, sir.
Yeah, that be 4.
Yeah.
But sir
No,
have 2.
it's up to sir. It's up to sir. It's up to sir. Because decimal point's tricky, so it's up to sir.
No, I'm just saying, Basso, because him have 2.14 and 0.53, we just use those values.
Yeah, we are just using what sir have.
Yeah, but remember, so we did round off, you know, so it's going to give 1.1.
Yeah, with the round off. But them said just using sir values, it would have been 1.13. So yeah, we could just use sir values. Granted, if you're taking your notes and you put the 3 decimal places, just make sure you put in your notes the 3 decimal places.
Like Sir
I
Sir
won't go
John.
on.
Sir tired away. Who over participate?
I'll never decimal place in a month.
Sir Pedro.
Who over participate?
You can't use calculator at the man.
Wait, the thing's still record? Oh, it's recording.
Are you still with me? I don't know. It seemed like I lost you guys for a minute. Are you there still?
Yes, sir, we're still here.
Okay.
It's like you disconnect there.
I was there talking like hell. Are you still seeing my whiteboard?
No, sir.
No?
You disconnected, sir.
All together? All right, let me.
Sir, may I say just as me start understand, you just left.
Yeah, right. All right, you should be seeing my whiteboard again.
But sir, you cut left way.
All right, are you
Yes,
seeing
sir.
my whiteboard again?
Yes, sir.
All right, so what I was saying is that based on what we had before, this is where we would be. We work out the resistor values to get this expression, and then we simplify this expression to get this, and we simplify that expression to, and we're down to this now. Everybody, because you were supposed to be working it out, not me. I gave you as a problem, but as usual, I am now doing your work. So everybody should be here. Tell me when you get here.
In our defense, sir.
Yeah. Tell me when you get here, because I don't want to just do the work and you haven't seen how I got here. Tell me when you tell me. So remember, we're coming from here, We just use the resistors, plug the resistors into this equation, and we were working them out, and we got to here.
Sir, when I did the thing, sir, the VCM for me perfectly cancelled. Whenever I run it up or nothing. So mine was just the 1.136 VD.
All right, well, you do it like me, because
Repeat that, sir.
Again, we're going back to this. You got a 2.14.
I used the 2.136, sir. 3 decimal place. I guess that's why mine end up like this.
2.14 times. If that was the case, you're gonna have to do it also with the
No, sir. That's it, sir. For all of them, I made all my decimal points 3 decimal place.
Okay.
Just end up down here.
Times. All right, so this is where we are, and this is what we get. I'm moving quickly along. What you should realize by now, ladies and gentlemen, is go back to the general expression for every operation amplifier for the output voltage. So the output voltage general expression is what? I should write it this way for you to help you see now. AD times VD plus
ACM.
I said it now, sir. I said it.
It's all going now. ACM.
I'm sorry, I don't know, sir.
All right. Times VCM.
Things are going, sir.
Okay. So what you realize, you should realize, ladies and gentlemen, is that you can simply now look and say, okay, based on the coefficient of what we got when we did our calculation, it clearly shows that AD is what?
1.14.
All right. And ACM is? Oops.
0 minus 0.01.
Where's my pen? And ACM, I like that answer. ACM is equal to?
Negative 0.01.
0.01. Not negative. You know why it's not negative?
No, sir.
A negative gain would be a what? A negative gain would be what?
Decrease.
A negative gain would be a loss.
Loss, that's the word.
A negative gain would be a loss. And there's no amplifier that is going to give you a loss. It's either it's not going to give you an amplification. You buy it? It's either it's going to, you put it on. So wait a moment, let me put it on. Yeah. So now we're in business because now we can find the CMRR. Because that is simply AD over
ACM.
ACM. Oops, ACM. Oops. And therefore, you know the values, you put them in, and you know that's the CMRR in dB is going to be 20 log of whatever you would have gotten when you put in your values. That I'm not going to put in for you. You must can do that yourself. Any questions?
Sir.
All right.
For like me who did mess up the calculations and get a zero DCM, would have to start over from scratch.
No, the question, if you get something like this, the question would never be phased that you get like that. It would be properly put together. That I just choose some values out of my head right now, but it would have been properly put together. And I tell you why.
Oh.
If you got 0 for your ACM, it means that you would have a perfect, probably too perfect of an operational amplifier. Because what it would say is that you're amplifying everything that is different, and you're getting rid of everything that is the same. Right. So it means that you'd have had your CMRR would be infinite. It would be so perfectly perfect that it is actually amplifying everything that's different and getting rid of all your noise or anything that is. That's what it would be saying.
So that is the ideal situation for a common mode.
I'm sorry?
That is the ideal.
Ideal, exactly.
For a common mode.
That would be ideal. All right. If there's no more question, I'd like to move.
Sir, just a quick question. Are you going to give us like a what you call it? Like a sheet, like a problem question sheet?
You mean like something like tutorial? That's what you're talking?
Like a sheet with questions and their answers so that we can practice, or we must just look it up in a textbook.
You have chapter 10 on the textbook?
Okay, I'll refer back to that then, sir.
Okay, wonderful. You have more than enough problems there with answers at the end of the book. Good? So, I mean, that's what I'm saying to you guys. I'm giving you guys everything. It's just a matter of whether or not you're actually utilizing it as efficiently as you can, or even simply efficient. Remember, you're now at a university, and most of the times, I can tell you, when I was a student, guys, I didn't get anything like this, and I didn't have any when I was at university back in the days before most of you would have been born. There was no internet for us. At least internet was just coming on stream for us to go and get these information. You had to go source textbooks upon textbooks and nights you're reading for every subject and finding the information. Nothing you just type or say to Google and you get things coming up. And therefore, it means that you have the world at your hand. And there's no lecturer who was spending any time giving you anything than just giving you the work. And then, I don't know how you guys would survive because those times you got.
Sounds very rough.
Well, it was the thing to do at the time. You might consider it rough. And probably at the time when I was still learning it, I would have considered it rough and probably the lecture been wicked and all that. But it was a good baptism into making sure that the information becomes common knowledge in your head. Because you'd have had to read, decipher for understanding. I do not necessarily want to give you information just to regurgitate. It doesn't work. It doesn't help you guys. Believe you me. All right?
Understood, Mr. Sir.
All right. So let's move on. If there are no questions about this, we can move on. Mr. Thompson. Delroy has abandoned me?
Yes, sir.
Oh, you're still there? All right. I'm picking on you this evening. I think I've given everybody the opportunity to share. I want you to share your screen, Mr. Thompson, just like you did the other day, because we're going to look at what it's called. And I want you to share the PowerPoint that I created, right? I want you to share the screen. Open it specifically to...
With the text, sir.
No. You remember the PowerPoint, right? I want you to go to Summon Amplifier. Do you understand what I mean?
Yes, sir. The one that with the combination of the signals from each
Right.
current from the.
So are you there?
I am still here, man.
Oh, I thought my thing disconnected.
So, you want me to stop sharing my screen so Thompson that you can share yours?
Yes, sir.
All right, so I've stopped sharing my screen. You can go right ahead. Again, this is something that you guys all have. This is something that I presented already. In terms of the PowerPoint. So we're just gonna use it to show you guys something. All right. Right. It's kind of small. Is want to maximize the screen that I can see. Now I'm seeing it. There you go. All right, this is the next thing we want to look at, ladies and gentlemen. Are you all seeing Mr. Thompson's screen?
Sir.
Yes, sir.
All right. We're gonna be looking at what is called a summing amplifier. Remember, we just look at the subtracting the difference amplifier. No, we're summing. This is a picture of a 2-input summing amplifier. And we can have up to n amount of input that are summed. Yeah? Now, if you notice this, it looks exactly like which one of the amplifier we've done so far.
Inverting, sir.
Exactly. We have looked at the inverting amplifier, but in that time we had only one input. Now, we're actually looking at the amplifiers with 2 input. Okay? But notice that the 2 inputs are connected to the inverting input. And in this case, the non-inverting input is grounded. So it makes this to be still an inverting amplifier. Now, based on that, if we should look at the circuit, we're applying an input V1. When we apply a voltage V1, we're gonna have, and I want, for your ease of understanding, I want you to change some of the numbers so that it becomes easy for you to follow. So we're gonna let this resistor here on V1, let that resistor be R1. Okay? And I want you to let the feedback resistor be RF. Hence, we're applying voltage V1 to input 1. It means that we have current I1 that's going to flow through the resistor R1. R1 is coming in. Look, we say we're changing this to R1, right?
Yes, sir.
All right. So we have I1 that is right at this point, right? Coming out of R, supposed to be R1, right?
Yes, sir.
Cool. What about when we apply a voltage V2? That's going to cause I2 to flow through R2, right?
Yes, sir. And then the two of them going to meet up.
Right. So right at this node, I1 plus I2 is going to be the current that is flowing now. At this point, right at this junction.
Yes, sir.
So we call this current here. You can call that current right that's flowing towards this virtual, remember, virtual ground. We can call that current now IT because it's a summation of both input currents, right?
Yes, sir.
All right, good. So we know from what we've done before that is going to go amplified and outputted. So we have an output current that's going to be fed back. Yeah?
Yes, sir.
It's going to be fed back through RF. Remember we said changing this to RF, right? It's fed back to RF. So we can say from what we know from what we did before that IT, which is the total current, is going to be equal but opposite to I3, or if you want to call it IF. So that's the feedback current, right?
Yes, sir.
Yes,
Cool.
sir.
All right. So let's write this in terms of, let's write a current in terms of voltage and resistance. So would you agree with me that if IT equals I1 plus I2, we could say then, in terms of voltage and current, voltage and resistor, we could say that IT really equals to V1 over R1 plus V2 over R2.
Yes, sir.
Cool. And that's going to be equal to minus VO over RF.
F.
Everybody following me so far?
Yes, sir. Yes, sir.
That's one like just one person.
Wait, sir, you say minus V over RF, right?
Yes. VO is the output voltage, and that is the voltage that's going to be divided by the resistor that is being fed back. So we could say it's VO over RF, right?
Yes, sir. but wait, sir. If they were equal, then sir.
So let's go to my whiteboard just to make sure that we're getting it perfect. So I'm giving you one more clean sheet. So we're saying that
Sir, did you send the whiteboard link before?
Oh yeah, you didn't send the link, sir. Or I was just looking on your screen.
Yeah.
But since they're already sharing the screen now, we can see what you're doing.
Okay.
If you can send Delroy the link, sir, and he just gets onto it, so we should be fine.
No problem. I don't even need to share link, because what I'm talking about is I don't even need to write anyway. Because what I'm saying is very straightforward. What I'm saying is if you go back to.
Oh wait, sir. What I wanted to ask is, since this current is being fed back, sir, wouldn't it start to oppose IT?
That is why it's minus.
Oh, okay.
So remember, I made the statement that IT is going to be equal to minus IF, which is the feedback current, right?
Yes, sir.
And all we're writing now is IT and IF in voltage resistor format. So we're saying that IT, which equals I1 plus 2, is really going to be equal to V1 over R1 plus V2 over R2. That now is going to be equal to minus VO over RF. Yes.
Mm-hmm.
So that's what we have. So if we want to find what would be the output voltage of this network, based on the equation that I just told you, rearrange that equation and tell me what V out would be.
V out equal minus IT times RF.
No man, remember we are now writing all the in terms of voltage and resistor.
Everything.
Oh, okay. So
what would be VO?
Minus RF times V1 over R1 plus V2 over R2.
Excellent.
go again with that.
VO will be equal to minus RF times in bracket V1 over R1 plus V2 over R2.
Okay.
Everybody seeing and getting that?
No, sir, we're not to get that.
Sure, it's a minus RF bracket.
Yeah, minus RF.
Yeah, MG.
Minus RF.
The equation again?
Oh, yeah.
You gotta come up with the equation yourself. Nobody no need to tell you. you come up with the equation and tell me what V out would be. Because I want you guys to independently understand. I don't want somebody to tell you you don't really see it. I have
I stepped away.
a guide you to the point where we said that IT equals to minus IF or I3 if you wish. But remember, IT equals to what? I1 plus I2. Okay? What about the feedback current? The feedback current in terms of voltage and resistor, what would that be?
IF.
What would that be in terms of voltage and resistance? What is IF in terms of voltage and resistance?
Sir, V1 over R1. That you mean, sir?
Minus V over RF.
Yeah, in terms of voltage and resistor, how would you express IF?
IF equal V over RF, sir.
Exactly. There is the current that is being fed back. IF or I3 if you wish. Current equals to what? Now voltage over resistance? What voltage would we have being fed back?
Output.
VO, sir.
VO. What resistor?
Feedback.
The feedback resistor. So therefore, IF in terms of voltage and current, sorry, in terms of voltage and resistor would equal to VO over RF, right?
Yes, sir.
Good. So now, if we write in the expression fully in terms of voltage and resistance, from the input side, we're going to have V1 over R1 plus V2 over R2, which is going to equal to minus VO over RF. Is that correct?
Yes, sir.
So I'm saying from that, I want to know what would be my output voltage. From that expression, what would be my output voltage?
So, no, sir.
But what Pastor said would.
Steel, you see pre-steel?
Oh yeah, man. Me get it.
You get it now?
You said that.
So tell me what it is now, no, man. You get it, but you don't tell me.
Sir, never else you wait for me.
Man. Now wait for anybody who didn't get it, because it's not for you, it's not for Mr. Thompson, it's not for Mr. McFall, it's for everybody.
All right, sir.
So your output voltage would be?
So I'm going to give a general equation first, and then so it'd be minus RF times IT, and then IT would be broken down. It'd be V1 over R1 plus the independent current, sir, from each source. So V1 over R1 plus
forget
V2.
about the current now, because the currents are being expressed in voltage and resistor.
Yes, sir. So V1 over R1 plus V2 over R2, sir.
Okay. So what we're saying is that this network called a summing amplifier, you can see that the output voltage is a sum of the individual input voltages. Are you seeing that?
Yes, sir.
The output voltage for this network is a sum of the individual, some coefficient, yeah? But it's a sum of the individual input voltages, V1 plus V2 plus V3 plus V whatever it is, right? As a matter of fact, if all the input resistance were the same, then we could write a general output equation to say that V out equals to minus RF over R, because R, remember, all the resistance would be at the input would be equal. So we could just say VO equals to minus RF over R, where R equals to R1, R2, R3, R4, where R equals to R1, which equals to R2, which equals to R3, which equals to R4. All I'm saying is that if all input resistance were equal, then we could have said that VO equals to minus RF over R, open bracket, V1 plus V2 plus V3 plus whatever other input voltages that you would have had. So this makes it clear to see that this network is considered a summing amplifier because the output voltage is some coefficient of the individual input voltages. Okay? All right. We have 9 minutes left. I'm going to look at two more quick circuits or networks. One, we want to find all right, so Thompson, thank you so much for sharing. I'm gonna you can stop sharing your screen now. Thank you. Oh Lord, and stop sharing and him actually leave the meeting. All right. So if I do this, it means that you should now be seeing again my screen. Tell me if you see my screen, which is basically a blank whiteboard.
Yes.
All right. Good. So, be that as it may, if I have, and pardon my drawing because I'm using my mouse, which is not necessarily, I should have been my stylo, but if I have a network like this, this is a non-inverting input and an inverting input, and I'm applying a voltage, of course, VI, on my inverting input. And I'm doing that through a resistor as usual. That's going here. So let's call this resistor RI to show us an input resistor, right? This is RI. Of course, always I have my non-inverting input grounded because I'm not applying two input signal and I'm not interested in having positive feedback. But of course, because I don't want to operate in the open loop configuration, I'm going to feedback some of my output to my input. So I'm gonna feed. Of course, I'm gonna have a feedback, and my feedback. Oops. Well, doesn't matter. My feedback mechanism that I'm gonna be using in this case, I'm gonna be putting a capacitor. Let's put a capacitor here. Okay. So this is C, a capacitor here, and this is my output. I should probably do this just to make sure it's more consistent with what you would have seen, even though it doesn't make a difference. So this is my input voltage. Let me make sure that you guys are seeing this clearly. This is my input resistance, a resistor, Ri. Okay. All right. But it's seen clearly, right? Again, we know that this point is our virtual ground, right? And that is because, different color. The feedback current is going to equal an opposite to the input current. Okay? So this is my feedback current. So if I apply input voltage here across this resistor, it means that this is my input current. Agree? And I can call it I. And this is my feedback current that's going through our capacitor. And I can say this is my capacitor current. And I can call this IC. Okay? We know from what we have that if we apply this input voltage, well, one thing we know for sure is that due to virtual ground, everybody is still there?
Yes, sir. We're still here.
All right.
Yes, sir. Yes, sir.
Sound too quiet, man. Let me think.
No, man, we're active, sir.
All right, so II, from what we know, II equals to what? In terms of the equals to minus, in this case, IC. Because IC is the feedback current, right? Because of virtual ground. And by now, everybody's supposed to know that. We're supposed to know that by now. No question asked. But we can express these currents in terms of voltages, right? So we can say II would be VI over.
All right.
Yeah, man. That's what I want you guys to sound. I think that I'm not talking to myself. You guys want to fall asleep?
Thank you on that, channel, my learn, sir.
All right. Good. So VI over II minus, what's the current? What's the current here in terms of voltage? Well, the voltage for sure is VO, right?
Yes, sir.
Yeah.
Okay. Well, here's something interesting.
Don't capacitors block
Sorry, what are
current
these,
flow? Yeah, don't they block current flow? What was the
Capacitor block current?
Store.
charge?
The capacitor will block only if it's DC. But our VI is AC because the DC was already used assumingly, to bias the transistor. So now we're applying actually real signal for amplification purposes, right?
Okay. Yes, sir.
How do you define a current through a capacitor? This again goes back to network.
But Q is equal to IT. Q over
V times voltage times farad.
You guys
Sure.
are Dr. Isaac.
Sure. You could use that.
Dr. Isaac Spurgeon.
Sir, DVDT, C times C.
Somebody's
Yes, sir.
What do we know? Well, I should probably ask you. Again, I don't want to pick on you to say, well, you know, you guys are, and you should know or shouldn't know or whatever. That's not my objective, eh? My objective is really, if you know, you do. If you don't, you don't. So
Sir,
current, because of how a capacitor is, the capacitor takes time to charge when you apply a differential voltage across it, right? So
Yes,
the
sir.
current will start, as soon as it charges, the current will start from 0 and it will increase, right? Up to the maximum possible current, right? After the capacitor has charged, right? So therefore, the current is going to be across the capacitor is going to be at the rate of change of the voltage, right? When we talk about rate of change, what does that mean? Or if you can remember that voltage equal to C times voltage equals to Q over V, right? Where Q is what?
Charge.
Right. So that's what we're saying. It's going to take a time to charge. So, and a little side note for right here now, just to make sure that we're all in the know. Sorry. We know that the capacitance of a capacitor. Where's that? That's outside. Angie, that's outside. I hear something like a voice. All right. So remember, C equals to what? Q, which is the rate, which is charge over V, right?
Yes, sir.
Okay. Therefore, the current through the capacitor, IC, will equal to the capacitance times the rate of change of the voltage. Because remember, we said that the voltage is going to start, and then the voltage is going to increase, right? For across the capacitor, right? Because remember, the capacitor is charging, you know. That's why I have this thing. Q, the capacitance is Q, which is the charge over the voltage, right? Yes?
yes, sir.
Right. And then we know that the current, and again, as I said, that is going back to network, that the current through a capacitor is going to be the rate of change of the voltage times the capacitance value. Okay? So let's go back to what we had. Since we know that II is going to equal to minus IC, but IC equals to what? C times.
DV over DT.
Right. All right. I hear the voices, man. You guys see, are my bright student now. Okay. Cool. So if that's the case, and of course, which DV we're talking
sir.
about here?
Sir,
This would be
I was
must
just
be a
about to
rate of change
ask
of
you.
the output voltage, right?
Yes, sir, that would be the output voltage.
Exactly.
Mhm.
So if we want to know, express what our output voltage would be for this network, we will have to boom, cross multiply, and when we cross multiply, we will see that this is going to be what? VI, first of all, yeah, over what? Actually, minus VI over RI times C and that actually is going to equal to what? dV
DT.
Over DT.
over dt. Okay. Cool. That's fine. We're getting somewhere. But we want VO. So how do we find VO? dV dt is what? The differential.
Differential.
Right, it's the differential of the output voltage. So if we want to just get the output voltage, what would we have to do? If we want to get V and not the differential voltage, what would we have to do to get V from this expression?
Integrate it. Yeah.
Brilliant. See? I must keep the class later because you guys are getting smarter when it's getting close to the end of the class. So if we integrate both sides with respect to t, right? So it means that from here, we're going to say that VO, right? Output voltage with respect to time is going to equal to what?
Minus VI.
Minus
RI.
The integral.
1 over R I times C, because those are constant, right? The only thing that's changing is the voltage with respect to time, right? So it's going to be Ri times C, yeah, times the integral of VI
With respect to T.
with respect to T. Okay? Yes. So what have we discovered, ladies and gentlemen? We've discovered the output voltage for the special circuit. The output voltage for this circuit, yes, is what?
Sir, the formula we just read for VO with respect to T.
Yeah, but what does it mean? It means the output voltage is some constant times the integral of what? The input voltage, right?
Yes, sir.
Which makes, so we're saying that the output voltage is, we can't forget about the constant for now in terms of, but we realize that the output voltage is an integral of the input voltage. You see that?
Yes, sir. Yes, sir.
Which makes this network an integrating amplifier. Or, simple put, an integrator. That's what this circuit is. That's what this network is. So you see, we are developing these networks, ladies and gentlemen, and the formulas from first principle. Lastly, based on our objective that we had set out for today, and I know that I'm running behind time, but you're going to see this one very clearly now. So next slide. This time we're having the same network really, but now we're changing the positions of the resistor and capacitor. So now, again, we have VI, but this time we're going to have a capacitor on the input. Yeah? And we have a resistor in the feedback network. Ground, of course, as usual, or input, or non-inverting input. So this is going to be a VI. This is RF as feedback resistor. And this is our output voltage, of course. Again, pretty much because of what we know, these two currents are going to be equal and opposite. So what would be the current? Because this is a capacitor. Again, what would be the input current? Well, first of all, this is, again, this is IC, right? Because it's going across a capacitor. And this, in this case, so is IF, because it's been so therefore, from what we know, clearly, IC is going to be equal to minus IF. Writing them in voltage format now makes it easy now because we know what voltage to what current to a capacitor is. Remember, it is C D V
over DT.
dt. But this case, which voltage are we differentiating? Which voltage is changing with time?
The input voltage.
I.
Our input voltage.
Yes.
It's dVi dt. And that's going to equal to IF, which is minus VO over RF. So from this expression, how do we find the output voltage? Pretty easy this time. Pretty easy, right? The output
Yes,
voltage
sir, just
transpose easily now. So VO is going to equal to cross multiply. So this is going to be equal to minus
Times RF.
minus RF times C. RF
Yeah.
times C. RF times C, yes? Times what?
dV
Differential
over dt.
of the input voltage with respect to time. Right? So put dV dt, right? So output voltage equals to minus what? Some constant, which is RF times C, the rate of change of the input voltage. So again, this is saying something. It is saying the output voltage for this network is the differential of the input voltage. Yeah? Times some constant. I should make this be smaller just to make sure that it is. Sorry. So this, ladies and gentlemen, we can clearly say that the output voltage for this network is a difference of the input. It's a rate of change of the input voltage, which is the differential of the input voltage, which makes this network, as you can figure, a differentiator, right? Because we're saying the output voltage oops. Anyway, I get a picture, right? Differentiator. You can spell it out when you're ready. So we have looked at the integrator, the differentiator, the summing amplifier, and the subtractor. Or the
Wait,
differential
sir,
amplifier.
can you repeat what you said? Middle signifies that it's a differentiator, the minus RF in the.
Come on, we're saying that
Oh.
output voltage, yeah? The output voltage of this network is the differential of the input voltage, you see? dV dt. While the other way around, the output voltage here, VO, is the integral of the input voltage, which makes it an integrator. So this is an integrator, and this is a differentiator. And by deriving the expression, we can see how we combine them. So there's no need to guess which is which. Even though all we're doing is playing around with the changing or exchanging the resistor and the capacitor. So with the capacitor being in the feedback loop, yeah, that, and the resistor being in the input loop, that makes it an integrator. And when the capacitor is in the input and the resistor is in the feedback loop, that makes it a differentiator.
All right, thank you, sir.
Here ends the reading of today's lesson.
Sir, I have a
If there are
question.
no questions,
I have a question, sir.
all right. What's the question, sir?
In terms of applying this formula to a calculation, sir.
A calculation, okay.
For dvi over dt, sir. Will it be Vc over t?
T over T? I don't
Yes.
If you're talking about the calculation, and we'll have plenty of that next time.
Okay.
For this circuit, the output voltage has to be minus RF, which you're gonna guess as a value, times C. You're gonna realize something soon, and you should probably realize it again from network, but I'm not assuming anything. That any times you have R times C, whatever R is, that's really a time constant.
Time constant.
So it's gonna be RF times C, yeah, time the differential or differentiating the input voltage with respect to time. So if you're given that the input voltage is a sine wave, it means that you're gonna have to say minus RF times C times the differential of your sine function. And when you differentiate sine, what do you get?
Cos, sir.
Custom.
I'm not even going to respond. I'm leaving it there so that you guys do your research, that when we come back to the next class, you're fully ready and sharp. Also, look again at the video. Look again. The notes that I've sent you, and we're gonna see how it is that, boom, we actually have enough practice questions. Ladies and gentlemen, you also have the textbook with questions and examples. Please utilize them. The next time we meet, we'll be looking at a couple of examples, and we'll be moving quickly along. We'll be looking at, again, it is posted, more in-depth knowledge of another application of Operation Amplifier, which is going to be one, your comparator. We're also going to be looking at how the Operation Amplifier can be used to create an analog to digital converter and also a digital to analog converter. So you have the information. It's already posted. You know, because I told you that's what we're going to be looking at. I'm expecting, ladies and gentlemen, that you're going to be spending some time. Have a look. Come to the next class session. Ready to go. With things that you would have learned or garnered from what you have read. Questions and concerns about things that you did not clearly understand, and things that the main takeaway from what you would have learned in regard to the specific things that I told you we're going to be looking at the next time we meet. Are you clearly following me?
Yes, sir.
Yes, sir.
Yes, sir.
All right, we're leaving it there for tonight. Have a good night.
Sir.
And as usual.
Wait, sir.
be
Delroy
safe,
calling
all right?
you, sir.
Delroy had a
Delroy
question.
calling you. Yes, sir. He's calling you.
Yes, sir. One question, sir. So it was about because we had some trouble with one of the classes, so I was wondering if you could tell me the topics that we had covered for one of them. So I'm trying to organize my notes.
I'm lost. I'm not sure exactly what you mean. Anything that I would have done in this class, I've done it in the Monday class as well. So this class is a little bit ahead of the Monday class. And we started looking at operation amplifiers, pretty much what they look like, how they are designed, how they're made up, the principles, the concept that they are fabricated in integrated circuit. How do you look at the integrated circuit in the real world in terms of how the pins, what the pins stands for? We started to look at the different input configuration of the operational amplifier. We looked at the different modes. We looked at what is called the different input modes. We looked at the practicality of some of these circuits. We looked at some of the applications. So we'll start with the integrator. Sorry, the inverted amplifier, non-inverted amplifier. We derive all the configurations, and we saw some more tonight. We looked also at inside of the operational amplifier, what it looks like in terms of the basic circuit, and also its DC equations and configuration. And we're going to be moving on the next time to what I explained earlier that we're going to be doing. So I hope that answers your question.
All right, thank you.
You are welcome.
Yes, sir. Thank you.
All right, sir.
All right, have a good night, everybody.
Sir, what does say about analog a while ago, sir?
Analog?